Thanks for tuning into this Revision Zone Maths video. In this video, we'll be looking at examples of being able to use the product rule. So let's try the very first example. We're given a function, y equals x squared, open brackets, 2x plus 5, and we have to try and differentiate it. So of course, in the past, we would have just expanded this. So we would have taken the x squared inside the bracket. We would have got a polynomial type function, and then we'll differentiate each term at a time. But now we want to use the product rule. So I'm going to write the function y as a function u times v, where u is going to be the first thing, which is here, x squared. So u is my x squared, and v then has to be the term in the bracket. So v is 2x plus 5. So this choice of u and v means that our function is exactly what we want. Now the product rule says that if I want to differentiate y with respect to x, I can leave the u, differentiate the v with respect to x, then leave the v and basically differentiate the u with respect to x and effectively sum them. So when I sum them, then the function I get in the end is actually going to be the derivative of y with respect to x. So to be able to do this, I'm going to need derivatives of u and v. So let me write them down here. So perhaps I can do that. If u is x squared, then du by dx is of course 2x, and if v is 2x plus 5, then dv by dx is basically 2. So once I actually have this, then that tells me that my dy by dx is nothing other than u. Well, we know that's x squared, so I'm going to write that down, times by dv by dx, well, that's just 2, add v, well, we know that's 2x plus 5, times by du by dx, well, we know that's 2x. So now it's just a matter of simplifying this, so I'm going to get 2x squared plus, and if I expand the bracket, I'm going to get 4x squared plus 10x. So again, collecting terms, I can say that's 6x squared plus 10x. So we actually have an answer. Now it might be worth very quickly just doing a check on our answer. So what we can actually say is we can go back to our function x squared 2x plus 5, and this time we can just expand as we would have done in the past. So we get 2x cubed plus 5x squared, and we can differentiate each term directly to be able to work out the derivative. So when we differentiate the first term, 2 times 3 is going to give me 6, and then I'm going to have x squared because I want to subtract the power of 1 from 3 to be able to get 2, and then the 5x squared differentiates to give me 10x. So indeed, we see that we actually have worked out the derivative in two ways, and we get the exact same thing. So example 2 requires us to differentiate the function x plus 1 all to the power 4. So let's again do this using the product rule, but this time using Newton's notation. So we want f of x to be written as a product of two functions, f of x, lowercase f of x, sorry, times by lowercase g of x. So we can actually make any choice of f and g we want, provided that when we actually multiply them, we actually get the function x plus 1 to the power 4. So in this case, to make life easy, we can say take f of x to be, say, x plus 1 to the power 2, and let's take that to be g of x. Okay, so as a check, then of course when we multiply them, f of x times by g of x, what we're going to end up with is we're going to end up with x plus 1 squared, because that's what f is, but g is exactly the same thing. Okay, so now because we have the same base, the base is x plus 1 in both those cases, when we multiply them, we can just add the powers, and we are going to get x plus 1 to the power 4, which is our capital F of x. So our description of the capital F of x is now in a sensible form. So when we have that, we're going to differentiate capital F. So we're going to say what the product rule actually says. So the product rule says, in Newton's notation, if I want to differentiate capital F with respect to x, then what I need to do is differentiate lowercase f multiplied by g, and differentiate lowercase g and multiply by f, and then effectively add them up. That's what the product rule says. So in this case, I'm going to have to differentiate my f. So let me take f here. So f of x obviously is x plus 1 squared. To differentiate this, I'm going to have to expand this. So I can just say x plus 1 times my x plus 1. And when I expand the brackets, I'm going to end up with x squared plus 2x plus 1. So that's fairly obvious, and we can differentiate this directly to say, well, it's just going to give me 2x plus 2. And of course, the beauty here is because g is defined to be the same function from above, are f and g exactly the same function, that's completely allowed. So I know that this is also going to be the same as the derivative of g. So you see, now I have my derivative of f and I have my derivative of g, and of course I know what my f and g are, so I can go write down what the derivative of capital F prime, sorry, what the derivative of capital F is going to be. In other words, the function capital F prime. So my f prime, obviously it's going to be 2x plus 2. My g is going to be x plus 1 squared, let's leave it in that form, and my g prime is again going to be 2x plus 2, and my f is going to be x plus 1 squared. So we can now tidy this up. Let me take out a factor of 2 from here and a factor of 2 from there. So I end up with 2x plus 1 times by x plus 1 squared, and I'm going to have the exact same thing repeated because the second term is exactly the same as the first term. If I can just squeeze that in. Yep, I've just got away with that, I think. Uh, so when we have that, now, just to simplify again, we see that we have the same base here, x plus 1 as here, so we can combine the power of 1 there with the power of 2 there. So I'm going to end up with 2 times by x plus 1 cubed. And of course, the second term is exactly the same as the first term I've just dealt with, so I'm going to have another copy of x plus 1 cubed. And now I can combine these because these are exactly the same. So I just add coefficients to get 4x plus 1 cubed. So we've managed to work out the derivative of capital F. Let's now very quickly check our answer. So perhaps I will just write down capital F is equal to, so let me say check here. So capital F is going to be x plus 1 to the power 4. Now I need to expand this. That's the only way we know how to do these sort of things from sort of year 1 A-level maths. So I'm just going to say, okay, by binomial theorem, I know it's going to be x to the 4 plus 4x cubed plus 6x squared plus 4x plus 1. So that's my capital F. And then when I differentiate this, I'm going to differentiate each term. So the x to the 4 is going to give me 4x cubed. The 4x cubed is going to give me 12x squared. The 6x squared is going to give me 12x. The 4x is going to give me 4, and the 1 differentiates to give me 0. But at this stage, what I can do is factorize out of 4, because the 4 is common to each one of these terms here. Right, 4 goes into 4 and it goes into 12, so I can take it out. So I basically get x cubed plus 3x squared plus 3x plus 1. But of course, again, by using the binomial theorem, we know that the entire thing in the brackets, so this thing here can actually be written as, this is a standard binomial expansion thing for a cubic. So I'm going to just end up with x plus 1 all cubed. So I've managed to work out the derivative directly. And we see that we got the same answer for the product rule as we actually get by differentiating directly. So example 3, we have another quite interesting function, x times e to the x, and we need to differentiate this. So let's jump straight in and differentiate it. I'm going to go back to using Leibniz notation again, just to be able to get some fluency with both using the Newtonian and the Leibniz notation. So I want to choose my u and v so that when I multiply them, I end up with x times e to the x. So I hope you would agree the natural choice is if I take u to be x and therefore v to be e to the x, then when I multiply u and v, I'm going to end up with x e to the x. Okay? So what does the product rule say in Leibniz notation? Well, it says you take your u, you differentiate v with respect to x, you multiply them, and then you take your v, you differentiate u with respect to x, and you multiply it by v, and then you add them up. And when you add them up, the answer you get is going to be the same as the derivative of y with respect to x. So we know that we're going to need both u and v, right? Because we need them there, but we also need the derivative of u and the derivative of v. So I'm going to have to differentiate u, and I'm going to have to differentiate v. So perhaps I can do that here. So since I know u is x, well then that tells me that the derivative of u with respect to x is just 1. That's a standard derivative. And since we know v is e to the x, that also tells me that the derivative of v with respect to x we can do. We've seen what the derivative of x exponentials is, e to the x differentiates to give us e to the x. So now that we have this, we can use all four of these with the formula here to write down the answer. So what's dy by dx going to be? Well, my u is just x, my dv by dx is just e to the x, my v is e to the x, and my du by dx is actually 1. So what we actually have is we have x e to the x plus e to the x, which we can of course tidy up by factorizing e to the x out. And we end up with this. So we've got our derivative here. Now, in the last two examples, at this stage we did a check using other techniques to see that the product rule technique actually works. But in this case, we will not be able to do a check like in the old case. The reason for that is because we don't actually know how to differentiate functions that are multiplied together, uh, how to check what their derivatives are going to be in an easy way. In fact, the product rule is precisely the technique we need to go to when we want to differentiate functions that are combined in this sort of a way. So we can't go back to easier techniques that we've seen as a way of checking what the answer is going to be here. Let's take a look at example 4. We have to differentiate x squared sine x. So let's write down a solution. Again, we've gone back to Newton notation. So we want to write f of x as a product of two functions, f times g. And again, the natural choice here is if we take our lowercase f to be x squared, and if we take our lowercase g to be sine x, then it's pretty obvious that when I actually do f of x times by g of x, what I'm going to end up with is going to be x squared times by sine x, which of course is just x squared sine x, which is precisely what we have as capital F of x. So our choice is actually okay for f and g. So once we've made that choice, we want to differentiate capital F, and the product rule tells me I differentiate lowercase f, I multiply it by g, and then I differentiate lowercase g, I multiply that by f, and then finally I add up the answer to be able to get the derivative for capital F with respect to x. So again, I'm going to need to know what the derivatives for f and g are. So let me write that here. So since f of x is actually equal to x squared, well that tells me that f prime x is just 2x. And since we know that g of x is defined to be sine x, then we've already seen in one of the previous videos that sine differentiates to actually give us cosine of x. So we've got that. So now it's just a matter of putting all this into the formula. Okay, so the first function is f prime, which of course I have here. So I'm going to write that down. I'm going to get 2x. The second function is of course g, which I have here. So I'm going to write that down, which is going to be sine x. Then there's a plus, and then the third function I want is g prime, which is here. So I'm going to write that down. So it's going to be cosine of x. And finally, the last function is going to be the f, which I have here. So I'm going to write that down. So it's going to give me x squared. And now it's just a matter of simplifying this, and we can just say it's going to be 2x sine x plus x squared cosine x. And that's basically our derivative. So example 5, we have a slightly more nasty looking function, x plus 1 all to the power 4 times by cosine x. But again, it's really much like what we've seen before. It's one function multiplied by another function, provided we can differentiate each function, we can differentiate the overall function. So sticking to our convention, we're going to try and switch to the Leibniz notation. So I want the function written as u times v, where u and v are functions in their own right. So let's take u to be x plus 1 to the power 4, and let's take v to be the cos of x. It's blindingly obvious that when I multiply them, I would get back to the function that I'm actually trying to differentiate in the first place here. So also I'll leave that as a check. But once we've got this, what do we know? Well, the product rule tells us that if I want to differentiate y with respect to x, I write the u, I differentiate v with respect to x, I multiply them. I write the v, I differentiate u with respect to x, I multiply them, and then I add them up. Okay. So that's the product rule. So what do we need? Well, I need to differentiate my u, and I also need to differentiate my v. Well, let's take a look at u. Now, this would take some thinking and working out the derivative of, but luckily we've already seen this as part of example 2 of this video, I believe. So from that, we just know that when I differentiate this, it's just going to give me 4x plus 1 to the power 3. And now going to v, which is cosine x, when I differentiate this, we've seen in one of the earlier videos in this series that the derivative of cosine is actually minus the sine function. So, armed with this information, we can basically go back to our formula for the product rule, and we can say, let's substitute things in. So what do I need? I need my u. My u is here, so I'm just going to write that down. So it's going to be x plus 1 to the power 4. And then I need my dv by dx. Well, my dv by dx is here, so I'm just going to write that down. So it's just going to be minus sine x, and then I have a trusted plus symbol, so I write that down. After which we actually need a v, so my v is here, which is cosine of x, so I write that down. So it's cosine of x, and then I multiply by the last term, which is du by dx, which is actually here, so I write that down. So it's going to be 4 times by x plus 1 cubed. Now we can tidy this up. Okay, so I'm going to end up with minus x plus 1 to the power 4 multiplied by sine x plus 4 times my x plus 1 cubed multiplied by cos x. And perhaps some people would like to write a positive term first, so maybe I can re-express the derivative by writing the cosine term first, just to make it look a bit prettier. So 4x plus 1 cubed cos of x, and then the sine term would come afterwards, which is x plus 1 to the 4 multiplied by sine of x. So we see we've actually managed to work out our derivative. So the next example ups the ante a little bit more. We now have to differentiate a product of two trig functions. This should be simple enough. So the only thing we really need to worry about is we have a product. Can we differentiate each part of the product? And if we can, then the product rule is there to be able to rescue us. So in this case, we definitely can, because we know how to differentiate the sine function and the cosine function. So let's write down capital F of x as lowercase f of x times by lowercase g of x, where, of course, in this case, it's fairly obvious what we're going to take our f to be. We can take it to be sine x, and we can take our g of x to be then cosine x. Okay, so with sort of this choice, we should be fine. So again, the product rule would say f prime of x would actually be, so I differentiate my f, I multiply by my g, and I differentiate my g, and I multiply that by my f, and I add them up. Okay, so that's our product rule. To be able to use this, I'm going to need to know the derivative of f and the derivative of g. So let's write them down. So since f of x is here, I wrote this deliberately in that place like so, then I know my f prime is actually the derivative of sine is cosine. We've already seen this before in one of the videos, and my g is here, so my derivative of g is going to be minus sine, because the derivative of cosine is minus sine. Okay, so now that we have that, I'm just going to substitute things into the formula. So let me do that directly. So my f prime is obviously cosine, so I'm going to write that down. So I've got cosine of x, and then my g prime, sorry, my g is indeed just a cosine, so I'm going to write that down again. So it's multiplied by cosine of x, and then I have a plus, and my g prime happens to be negative sine x. So let's write that down. So it's going to be negative sine of x. Let's put a bracket around this just so we don't get mixed up with a negative sign. And then I have the f of x, which is obviously just a sine function. So I can quickly write that down. So we have that. Now we can simplify this, and the first two terms are going to combine. Cos times cos is going to be cos squared. So I can just write that down. And the sine times sine is going to give me sine squared, but of course I've got to be careful with that minus. So what I'm going to do is I'm going to have a minus sine squared x, and this is basically our derivative. I will say quickly that obviously we've got to be careful. Let me just say it in red. This is not the same thing as, so cos squared x take away sine squared x is not equivalent to cos squared x plus sine squared x, which is obviously 1, right? So yeah, so that's just an aside. Perhaps we can't necessarily check this by using any standard trivial method. What we can do is do sort of redo this calculation as a way of checking. Define f as again f times by g, but because sine times cos is the same thing as cos times sine, because you can multiply things in different order and the answer doesn't change, let us now define our f of x to actually be not sine x but cos x. Okay? And let us now define our g of x to be not cos x, but let us define it to be sine x. So now in this case, again, the product rule is going to be exactly the same. So I'm going to have f capital F prime is going to be f prime x g of x add g prime x f of x. So I just need to work out the derivative of my f and g again, but I know what they are. So the cosine differentiates to give me minus sine, right? And the sine differentiates to give me cosine. And because we've swapped what we've defined f and g to be from what they were defined to be above, you can see that I started with a sine and a cos, but now I'm starting with a cos and a sine, and I ended up with a cos and a minus sine, but now I'm ending up with a minus sine and a cos. So that's just a sensible check to make sure I'm actually on the right page. So once we actually have this, in this case, we start to substitute things in again. So the first term here is f prime. Well, what's f prime? It's just minus sine. Okay, let me just make sure that minus is quite clearly visible. So I'm going to end up with minus sine x, and then what's my g? Well, my g is here, that's just sine x. So let me write down sine x, and then what's my g prime? Well, my g prime is here, that's just cos x, and of course I have a plus before that, so I'm just going to have cos x. And finally, what's my f? My f here now is just the cosine of x. So I multiply by cosine of x. So again, simplifying this, we can see that we end up with minus sine squared x plus cos squared x, which of course we can rearrange to say that's the same thing as cos squared x minus sine squared x. So in fact, we've just been able to show that swapping the description for what you call lowercase f and what you call lowercase g makes no difference to the product rule. So we've seen plenty of sort of examples of just direct standard applications of the product rule. Now let's start to get a little bit more creative with actually being able to apply the product rule. So in this case, we've got an even more involved function. We've got sine to the power of 4, and we want to differentiate this. So we're going to use, in fact, the product rule repeatedly here. So let's write that down. So a good start might be to split that sine to the 4 up as two separate functions, right? So I might write down that sine to the 4x can actually be written as sine squared x times by sine squared x, okay? So provided that I can differentiate sine squared, I should be okay to differentiate the entire function y, right? Because I've got sine squared and I've got the same function again. So normally to use the product rule, we need to differentiate both these functions. But because I've got the same function repeated twice, if I can differentiate it once, then I'm basically home. So let's now do another problem. So let's think about just being able to differentiate y equals sine squared x. Now I should be very, very clear here that the y I've written here is not the same as the y I've written there. I should use a different symbol, but I'm slightly conscious that if I use a different symbol, then some people are sort of somewhat emotionally attached to particular symbols. And if I have strange symbols here, they might not be very happy. So as long as you're clear that the two y's, the one in blue and the one in black, are not quite the same, we should be okay. So again, here I can rewrite the sine squared as sine x times by sine x. And that really helps because I know how to differentiate a sine x. So once I know that, I should be able to differentiate the entire thing, in other words, sine squared, by using the product rule. So what was the product rule say? So it will say if I have y equals uv, right, then my dy by dx is going to be u dv by dx plus v du by dx. Okay, so in this case, I can take my u to be sine x, and of course my v can be taken to be the exact same thing, and that would guarantee that my uv is actually sine squared x for the y in blue here, of course, right? So I need to be able to differentiate my u and v, so I can just say that from here. What I know is my du by dx is just the derivative of sine, which we know is a standard function, is cosine. And of course, that's the same as dv by dx in this case. So since I know that, I just go to this function, this product rule formula, and just put stuff in, right? So my u is, of course, quite clearly written here. It's sine x. So I write that down. My dv by dx, well, it's here, so that's cos x, so I actually write that down, multiplied by cos x. Then we have the add, then we have v, so my v is again just here, so I write that down, which is sine x again, and my du by dx is obviously here, so I write down the cos x again. So simplifying this, what we actually end up with is we end up with sine x cos x plus sine x cos x, okay, which obviously is 2 sine x cos x. I've just managed to squeeze that in. Good. So we've basically been able to differentiate our function in blue. So we've differentiated sine squared, okay? So now I'm going to go back to the function in black. So this is a different y, of course. So let me go back to y. So now let us differentiate y equals sine squared x times by sine squared x, right? So again, I say take y to be equals to uv because I want to use the product rule, but I've got to be very clear, it's not the same u and the same v as here. I'm just calling them u and v because the product rule is generally written in that sort of conventional way. Indeed, I've said this repeatedly, I'm using different colors to be able to distinguish between different functions. So in this case, because I want to be able to have the function sine to the 4, in other words, sine squared times by sine squared, I take my u and v to both be sine squared. Okay, I do that. Now, what's interesting here is if you see, what I've called my black u, sine squared, is the same thing that was my blue y. Okay, so when I now come to differentiate my du by dx, because I'm going to need that as part of the product rule, that is going to give me the same answer as when we differentiated the blue y. Okay, which we got to be 2 sine x cos x, right? So sine squared differentiated is 2 sine x cos x, and that's the same thing as dv by dx, of course, because my u and v are defined to be the same. So once we've written that down, let us write down the product rule again. So the product rule in this case would say dy by dx is equal to u dv by dx plus v du by dx. But of course, in this case, all the u's and v's are in sort of black, so they're different u's and v's to ones we've seen above. So what's my u? My u is sine squared x. What's my dv by dx? Well, it's 2 sine x cos x. And what's my v? Well, my v is basically again sine squared x, right? So I sort of see that clearly here. My v is sine squared x, and what's my dv by dx? Well, my dv by dx again is just here, so I'm gonna be able to write that down, which is gonna give me 2 sine x cos x if this would write. Okay, good. So once we have this, now it's just a matter of tidying the whole thing up a little bit, right? The unsurprising thing is we've got same sort of terms coming again and again. So here I've got a sine squared times by 2 sine x cos x, and at the bottom I have a sine squared times by 2 sine x cos x. Of course, the reason for that is my u and v are the same, so my du by dx and dv by dx are the same, okay? So basically what I'm going to have is the 2 here and the 2 there are going to combine to give me a 4 because they're being added. So I'm just going to write that down. So I'm going to have a 4, and the sine squared, indeed, times by the sine in both cases is actually going to give me a sine cubed. So I'm gonna write that down, and then I've just got the cosine in each case. So this is what I'm going to get when everything is simplified and we've managed to work out the derivative of our initial function, which was sine to the 4. So the next example has another rather interesting function. We do have a product, of course. We've got a function here. We can think of the 3 sine x minus 2 cos x as one function, and then we've got that multiplied by another function. And again, we can differentiate this directly just by using the previous rules of differentiation that we already know. And we, of course, know how to differentiate e to the 4x by previous rules of differentiation. So we can go and apply the product rule in this case directly. So let us take capital F of x to be lowercase f times by lowercase g, where our lowercase f of x can be defined to be 3 sine x minus 2 cos x, and of course our lowercase g of x can just be taken to be e to the power of 4x. Right, so when we have this, we know that when we multiply f and g, we're going to end up with capital F. That's really no problem, so this definition here is well made. So let's write down the product rule. Well, it says if I want to differentiate capital F, I differentiate lowercase f, I multiply it by g, I differentiate lowercase g, I multiply it by lowercase f, and I add them up, right? We've seen this lots of times now. So I need the derivative of lowercase f and lowercase g, so let's write them down. So this basically tells me that my lowercase f would differentiate. Well, I just go and apply previous rules that we know. We differentiate each term one at a time, and then we write down the derivative. So the derivative of 3 sine x is just going to be 3 cos x, because the derivative of sine is cosine, and the 3 just comes along for the ride. And the derivative of minus 2 cos x is going to be the derivative of cos is minus sine, and the minus 2 will come on for the ride. So minus 2 times minus 1 is going to give me plus 2 sine x. So we've managed to work out the derivative of f, and the derivative of g, of course, is very, very obvious. That's a standard exponential, so I'm going to get 4e to the 4x. So now that we have this, we have our f and g, and we have our f prime and g prime, we can just go to this function and substitute. So let's do that directly. So f prime is of course 3 cos x plus 2 sine x. and g is, of course, we have that here, so g is just e to the 4x, and then there's a plus from that, and then we need g prime. G prime is just here, so g prime is 4e to the 4x, and then we finally need the f. So the f is just there, so I'm going to write that down. So it's 3 sine of x minus 2 cosine of x. So now technically we are done. This is our derivative, this function here, but it's nice to be able to write this in sort of nicer simplified form. The important thing to keep in mind is there's an e to the x here, or e to the 4x rather, and there's an e to the 4x here. So perhaps what I can do is just factorize e to the 4x out of the entire thing. So I'm going to write down the terms that I actually have. 3 sine of x minus 2 cos of x, and of course I'm going to take out an e to the 4x. So I've taken out, as I've said, this e to the 4x from both those things, so it's ended up here, and the first bracket is just there, and the second bracket is just there, and there was a 4 outside the second bracket, so that's just left there. So let's combine everything in the big brackets. Well, okay, so I'm going to get 3 cos x plus 2 sine x. Now expanding this thing here, I can easily write down 3 times 4 is 12 sine x, and 4 times minus 2 is going to be minus 8 cos x. So once we have that, the e to the 4x is just on the outside, and at this stage we can start to combine the cosine with the cosine and the sine with the sine. Obviously, the 12 and the 14 and the 12 and the 2 is going to give me the 14, so I'm going to have 14 sine x. But then I've got 3 cosine, but I'm taking away 8 cosine, so I'm going to end up with my negative 5 cosine, and the square bracket is still there. And then we have e to the 4x. So this is our derivative. We've managed to work out our derivative. And again, it'd be nice to check this, but there's no easy way of checking this. In fact, as I keep saying again and again, to really emphasize the same point, that the whole point of the product rule is to actually be able to do these sort of calculations, which we wouldn't have been able to do in the past. So let's take a look at example 9. We've seen lots of examples now, some of which are quite complicated, so I thought it'd be useful to see something which is quite simple, but to try and understand some deeper aspects of what's happening with the product rule. So the statement in red says, the point of this example is to show that we have a lot of freedom in how we apply the product rule, right? So let's show that. In this case, our function is very simple. We have y equals x to the 4. So let's do it using two sort of choices. So let's say method one. Method's probably not the right word for this, what I'm trying to say, but let's just work with that now. And let's say the other one to be method two. And both of them are going to use the product rule, but the difference is going to be one of them is going to have a particular choice for u and v, and the other one's going to have another choice for u and v. Okay, so I want to write down my function y in the form u and v. So let me take u to be, say, x, and v to be x cubed in the first case, right? So x times x cubed is going to give me x to the 4. So that choice of u and v is really well defined. And in the second case, let me draw, say, a line here, and let me again say y equals uv. But now let me take my u to be x squared, and my v also to be x squared. So we've got two different choices for u and v in both those cases. Right, so let's do the sort of method one approach. So first of all, what is my product rule telling me? It's telling me if I want to differentiate y with respect to x, I can do that by doing u times by dv by dx, and then adding that on to v times by du by dx. Okay, so I need to work out what du by dx is and what dv by dx is. So I take these functions and I differentiate them. So I'm just going to write them down here. So du by dx is obviously just 1 because x differentiates to give me 1. And dv by dx is just going to be x cubed differentiates to give me 3x squared. Okay, so once I have that, I go back to the formula for the product rule and I basically substitute that in. So my u is x, so I write that down. My dv by dx is here, so it's going to be 3x squared, so I write that down. And then my plus is there, and then my v is basically x cubed, so I write that down. So I write x cubed down, and then my du by dx is basically 1, so I write that down. And then when I tidy this up, I'm going to get, for the first term, I'm going to get 3x cubed. So let's write that down. And then my second term is, of course, x cubed times by 1, which is obviously just x cubed. So when I put them together, I get 4x cubed. So that's what I get from method 1. Let's now do method 2. Again, same sort of idea, but I have a different u and a different v. So I'm going to write down the formula for the product rule. The product rule says that dy by dx in this case is again going to be u dv by dx plus v du by dx. Okay, so if I can only get the pen to work, good. So once I actually have this, obviously I need the derivative of u and v. So I'm going to say my du by dx is actually going to be 2x because u is x squared. And because v is effectively also v equals x squared, which is the same description as u, then dv by dx is also actually just going to be 2x. So now that I have all the things I need, let me go and put them into this formula. So my u is x squared. So let's write that in. So I actually end up with is x squared. My dv by dx is here, so that's 2x. So we put that in. So we times by 2x, and there's a plus sign, and then I have a v. So so the v is just here, x squared again. So I put that in, and finally I actually have du by dx, which is here, so which is 2x again. Okay. So again, simplifying this, we basically end up with 2x cubed add 2x cubed, which is 4x cubed. Now this is the point I was trying to make, which is even though we made different choices for u and v in our two methods, the product rule still works, and we got the exact same answer. We got the exact same answer in both those cases. And because our function is just a standard polynomial, we can actually do a check in this case. We can actually just say y equals x to the 4 is our polynomial. So we can just differentiate it directly using the rules we've already seen. And that's basically going to give us 4x cubed. So in fact, we know that the answer is also right. So I hope that showed you the freedom that we really have in being able to make choices for what we take our two functions to be when we're applying the product rule. And it is very possible that you can come across an example where you can't do it with the product rule if you make a certain choice, but if you go back and make another choice, then you would be able to use the product rule and be able to answer that question. So it's really, really useful to sort of have a good feeling for what functions to pick when you're actually applying the product rule. Let's look at the last example. The function in this case is x cubed. This is obviously a very, very easy function which we can differentiate directly, but I've chosen this example to try and highlight another subtle point about product rule. So the point of this example is to show that the product rule can be extended to more complicated cases. So let's work this out. So let me define my function f of x in this case, not as a product of two functions f and g, which is what we've been seeing so far, but as a product of three functions f, g, and h, right? In this case, I'm going to say take my f of x to be x, and take my g of x to also be x, and take my h of x to also be x. And of course, it's unsurprising that when I do f times g times h, I get x times x times x, and that gives me x cubed. So my description of the function capital F being lowercase f times lowercase g times lowercase h is actually consistent, right? So the question is, what would the product rule formula look like for a function which is written as a function as a product of three functions? And you can go away and maybe think about this, but what you can figure out is the product rule formula in this case is going to be f prime times by gh plus g prime times by fh plus h prime times by fg. So the key idea with the product rule is basically it doesn't matter how many functions you have here. What you do is you differentiate each function and multiply by everything else, and then you differentiate the second function and you multiply by everything else, and then you differentiate the third function, and then you multiply by everything else, and then once you've got all those things, you basically just add them up. And that's what happens when you extend the product rule formula to having more and more functions. So let's basically now apply this. So I'm going to need to know my derivative of lowercase f, my derivative of lowercase g, and the derivative of lowercase h. So I've written these f, g, and h above here conveniently so I can write down the derivative. So my f prime is just going to be 1, my g prime obviously is also going to be 1, and my h prime is obviously also going to be 1. So once I have that, I know my f prime is just 1, my g is x, and my h is x, and my g prime is 1, and my f is x, and my h is x, and my h prime is 1, and my f is x, and my g is x. So once I have that, I can combine these to say x squared plus x squared plus x squared, and that basically gives me, when I simplify, 3x squared. And of course, in this case, we can actually just check because our function capital F is actually already a nice polynomial function. So when I differentiate x cubed, we basically get 3x squared. So we can see that actually what we actually have here is we get the exact same answer. And this should convince you of the fact that the product rule can be extended to actually being able to allow us to differentiate very, very complicated looking functions. Because you can only imagine if I had something horrible where 3 or 4 functions were being multiplied, and but I can then pick the f, g, and h in a way where I can differentiate each one of those functions, and then I can use that formula to be able to differentiate the overall nasty function. Okay? So with that, I would like to bring this video to a close. If you found this useful, then please hit the like and subscribe buttons. Do comment in the comment section as to what you would like to see more videos on. Thank you for watching, and we will certainly see you in the next video.